In my Emerging Technology 1 project, I explored makerspaces. One piece of technology in my school's makerspace is a 3D printer. For this assignment, I created a lab activity centered around the 3D printer and moment of inertia. Moment of inertia, also known as rotational inertia, is a key part of second semester AP Physics. It is the rotational equivalent of mass, just as rotational velocity, which is represented by a lowercase omega, is the rotational equivalent of linear velocity. My lab is to give students a challenge of printing a shape with a certain numerical rotational inertia. Students can derive the formula for a shape of their choice. Here's an example of what that would look like with a uniform solid sphere. We begin with the inertia for a solid cylinder with a radius big R. As the mass increases, the moment of inertia for the cylinder increases. For a sphere, the radius is changing, so we must find dm with respect to dv. We find dv and substitute it in to help find dm, then we use that to help find di. After adjusting our variable with the Pythagorean theorem, we are now able to integrate. After subbing in the density and doing some simple algebra, we now have our moment of inertia. Of course, for students who are struggling with calculus, there is always the option of differentiating by giving them the moment of inertia to begin with and allowing them to proceed from there. After students integrate and find the moment of inertia for the shape that they want to create, they would have to set that expression equal to their given moment of inertia. Suppose they decide on creating a solid sphere that we found the moment of inertia for on the previous slide with a rotational inertia of 5 kilograms meters squared. They would first set that equal to 2/5 mr squared, which is the rotational inertia that we found on the previous slide. They would divide out the 2/5, so they would end up with 25/2 equals mr squared. They would substitute in d times v, which is density times volume, for mass, and then they would substitute in the volume of a sphere for v. So this would leave them only with r in their equation, and then they would be able to print that sphere on the 3D printer with radius r. And this works because we figure out the density of the material that the 3D printer prints with, and then we are able to use that to help us find the radius that is necessary without needing the other variables in this equation. There are obviously many more other options for using a 3D printer in education, so here's a video explaining some of those.
For me, 3D printing is more than just a subject in its own right. It's actually a catalyst for learning right across the curriculum. It's not just a design technology or an ICT technology. What it is a cross-curricular learning trig point. You know, whether it's a DNA helix printed in biology or a scanned wall being mapped for history use, then 3D printing really is a catalyst and a conduit for lots of learning opportunities. The Create Education project was launched earlier this year, and basically Create is an acronym of our core values: community, reliability, education, access, teachability and economics. And what it's designed to do is take away the headaches from teachers, so there is little barriers to the learning outcomes that can come from 3D printing. Speed of 3D printing, material of 3D printing and scale of 3D printing are the big areas of development. There's a lot of hype about whether it's the next industrial revolution or not. That is yet to be ascertained. What is unquestionably true is the change in people's mentality and their ability to make and create a solution rather than making do with what's currently on offer. The great thing with Ultimaker is that we're open source, so it's not just tied to what Ultimaker themselves are doing. We have a very active community that's constantly participating in R&D. So the latest installment of the Cura software, which is our slicing software that we use to create the 3D models once they've been designed on CAD, has actually been developed by 3 people who are passionate hobbyists, aren't employed by Ultimaker. Their updates have been incorporated into the official software, which has now been shared worldwide. In terms of the actual home-based applications, there needs to be some development, but we're already looking at conductive and non-conductive materials, soluble and non-soluble materials, and then there's also big advancements in biomedical and nano materials as well. And I truly believe the integration of that science, coupled with advances in the hardware of 3D printing, will make it very accessible for the home user. I'm not sure that we'll ever be able to replicate humans per se due to the complexity of our DNA, etc. But in terms of being able to replicate and transport digital information from one terminal to another so that a model can be produced, we're not a million miles off already.
As you can see, there are so many more cross-curricular options for other sciences, histories, math, or even art. I hope you are inspired to use 3D printing in your classroom. Thank you for listening.